A heat engine is any machine which converts heat into work. It takes heat from a high-temperature body, which is called a thermal reservoir, extracts some work, and then gives the remaining heat to a low-temperature body. Thermal reservoir is an ideal concept in thermodynamics. Just like how a water reservoir or dam stores water, a thermal reservoir stores heat. Similarly, like a dam seems to provide an infinite amount of water without becoming dry. A thermal reservoir provides an infinite amount of heat without losing its temperature. In formal definition, a thermal reservoir is a body of infinite heat capacity, such that its temperature does not change when heat is extracted from it or supplied to it. In thermodynamic calculations involving a heat engine, we use thermal reservoirs as a heat source and heat sink. No matter how much heat we extract or supply these reservoirs, the temperature remains constant. Work extracted by a heat engine is the difference between the heat supplied by the hot reservoir and the heat rejected to the cold reservoir. The thermal efficiency of a system is desired output by the input given. Here, our desired output is extracting some work. And the input we provide is the heat from the hot reservoir. But work output is the difference between heat supplied and heat rejected. So the thermal efficiency of a heat engine, denoted as E to TH, is equal to 1 minus QC by QH. For an ideal reversible heat engine, there are no inefficiencies. So, the amount of heat provided or absorbed by a reservoir is dependent on only one factor, that is the temperature. So we can say that the heat provided or absorbed is proportional to the temperature. Then QH by QC is equal to TH by TC. And so the efficiency of a reversible heat engine is equal to 1 minus TC by TH. A common question is, why is there a low temperature reservoir? Why can't we just extract QH as work completely? Or, why can't QC be equal to 0? This is where the second law of thermodynamics helps us. The only reason that the hot reservoir provides heat QH is because of the presence of a cold reservoir. Just like how in real life, heat only flows naturally from hot objects to cold objects, we need a cold object so that the hot reservoir will provide us some heat. For this reason, we will never be able to completely use the heat provided by the hot reservoir. There will always be some remaining heat that we reject. In other words, the efficiency will never be 100%. This statement is known as Kevin Planck's statement. It is impossible to make a cyclically operating heat engine whose effect is to absorb energy in the form of heat from a single thermal reservoir and to deliver an equivalent amount of work. Heat pumps and refrigerators are the opposite of a heat engine. So they are also called reverse heat engines. They are used to provide or extract heat from a reservoir by having some work done. If our aim is to heat up a body, then we call it a heat pump. If we're trying to cool a body, then we call it a refrigerator. Both work in exactly the same way. Some heat is extracted from the cold reservoir. Work is done on it, and a higher amount of heat is given to the hot reservoir. But since our objectives are different in both cases, the way we calculate their efficiency is different. Since we aren't extracting any mechanical work in this type of machine, we don't talk about the efficiency. Instead, we call it the coefficient of performance, or COP, which is the desired output divided by the input given. For a heat pump, the desired output is the heat provided QH, and the input is the work done. But the work done is the difference between the heat provided and the heat extracted. So, the COP of a heat pump is equal to QH by QH minus QC. For an ideal reversible heat pump, there are no inefficiencies. So, the amount of heat provided or absorbed by a reservoir is dependent on only one factor, that is the temperature. So we can say that the heat provided or absorbed is proportional to the temperature. Then QH by QC is equal to TH by TC. Using some clever transformations, we can express COP as 1 divided by 1 minus QC by QH, which allows us to use the earlier equation in this one. And so, the COP of a reversible heat pump is TH by TH minus TC. If the same device is used as a refrigerator, then the desired output is heat extracted from the cold reservoir, QC. And the input given is the work done, which is equal to QH minus QC. So, the COP of a refrigerator is QC by QH minus QC. For an ideal reversible refrigerator, there are no inefficiencies. So, the amount of heat provided or absorbed by a reservoir is dependent on only one factor, that is the temperature. So we can say that the heat provided or absorbed is proportional to the temperature. Then QH by QC is equal to TH by TC. Using some clever transformations, we can express COP as 1 divided by QH by QC minus 1. Which allows us to use the earlier equation in this one. And so, the COP of a reversible refrigerator is TC by TH minus TC. Here, we can see that, as the work done becomes smaller, the performance or the COP of the device will increase. So, if the work done approaches 0, then the performance approaches infinity. Or in other words, if we can extract heat from a cold body and supply it to a hot body without doing any work, then our COP is infinity. But we know from second law, and from common sense, that heat will never naturally flow from a cold body to a hot body. This is known as Clausius' statement. It is impossible to construct a device whose sole effect is the transfer of heat from a cool reservoir to a hot reservoir.